A Brief History of Time, written by Stephen Hawking, read by Akashveer. This is chapter number 8, The Origin and the Fate of the Universe, Part 3. One would feel happier about the anthropic principle, at least in its weak version, if one could show that quite a number of different initial configurations for the universe would have evolved to produce a universe like the one we observe. If this is the case, a universe that developed from some sort of random initial conditions should contain a number of regions that are smooth and uniform, and are suitable for the evolution of intelligent life. On the other hand, if the initial state of the universe had to be chosen extremely carefully to lead to something like what we see around us, the universe would be unlikely to contain any region in which life would appear. In the hard Big Bang model described above, there was not enough time in the early universe for heat to have flowed from one region to another. This means that the initial state of the universe would have to have had exactly the same temperature everywhere in order to account for the fact that the microwave background has the same temperature in every direction we look. The initial rate of expansion also would have had to be chosen very precisely for the rate of expansion still to be so close to the critical rate needed to avoid recollapse. This means that the initial state of the universe must have been very carefully chosen, indeed, if the hard Big Bang model was correct, right back to the beginning of time. It would be very difficult to explain why the universe should have begun in just this way, except as the act of a God who intended to create beings like us. In an attempt to find a model of the universe, in which many different initial configurations could have evolved to something like the present universe, a scientist at the Massachusetts Institute of Technology, Alan Guth, suggested that the early universe might have gone through a period of very rapid expansion. This expansion is said to be inflationary, meaning that the universe at one time expanded at an increasing rate rather than the decreasing rate that it does today. According to Guth, the radius of the universe increased by a million, one with 30 zeros after it, times in only a tiny fraction of a second. Guth suggested that the universe started out from the Big Bang in a very hot but rather chaotic state. And these high temperatures would have meant that the particles in the universe would be moving very fast and would have high energies. As we discussed earlier, one would expect that at such high temperatures, the strong and weak nuclear forces and the electromagnetic forces would all be unified into a single force. As the universe expanded, it would cool, and particles' energies would go down. Eventually, there would be what is called a phase transition, and the symmetry between the phases would be broken. The strong force would become different from the weak and the electromagnetic force. One common example of a phase transition is the freezing of water when you cool it down. Liquid water is symmetrical, the same at every point and in every direction. However, when ice crystals form, they will have definite positions and will be lined up in some direction. This breaks water's symmetry. In the case of water, if one is careful, one can supercool it. That is, one can reduce the temperature below freezing point, 0 degrees Celsius, without ice forming. Guth suggested that the universe might behave in a similar way. The temperature might drop below the critical value without the symmetry between the forces being broken. If this happened, the universe would be in an unstable state with more energy than if the universe had been broken. This spatial extra energy can be shown to have an anti-gravitational effect. It would have acted just like the cosmological constant that Einstein introduced into general relativity when he was trying to construct a static model of the universe. Since the universe would already be expanding just as in the hot Big Bang model, the repulsive effect of this cosmological constant would therefore have made the universe expand at an ever-increasing rate. Even in regions where there were more matter particles than average, the gravitational attraction of the matter would have been overweighed by the repulsion of the effective cosmological constant. Thus, these regions would also expand in an accelerating, inflationary manner. As they expanded and the matter particles got farther apart, one would be felt with an expanding universe that contained hardly any particle and was still in the supercooled state. Any irregularities in the universe would simply have been smoothed out by the expansion, as the wrinkles in a balloon are smoothed away when you blow in it. Thus, the present smooth and uniform state of the universe could have evolved from many different non-uniform initial states. In such a universe in which the expansion was accelerated by a cosmological constant rather than slowed down by the gravitational attraction of matter, there would be enough time for the light to travel from one region to another in the early universe. This could provide a solution to the problem raised earlier of why different regions in the early universe have the same properties. Moreover, the rate of expansion of the universe would automatically become very close to the critical rate determined by the energy density of the universe. This could then explain why the rate of expansion is still so close to the critical rate, without having to assume that the initial rate of expansion of the universe was very carefully chosen. The idea of inflation could also explain why there is so much matter in the universe. There are something like 10 million 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 million. It means 1 with 80 zeros after it. Particles in the region of the universe that we can observe. Where did they all come from? The answer is that in quantum theory, particle can be created out of energy in the form of particle-antiparticle pair. But that just raises the question of where the energy came from. The answer is that the total energy of the universe is exactly zero. The matter in the universe is made out of positive energy. However, the matter is all attracting itself by gravity. Two pieces of matter that are close to each other have less energy than the same two pieces a long distance way apart, because you have to expend energy to separate them against the gravitational force that is pulling them together. Thus, in a sense, the gravitational field has negative energy. In the case of a universe that is approximately uniform in space, one can show that this negative gravitational energy exactly cancels the positive energy represented by the matter. So the total energy of the universe is zero. Now, twice zero is also zero. Thus the universe can double the amount of positive energy and also double the amount of negative gravitational energy without violation of the conservation of energy. This does not happen in the normal expansion of the universe, in which the matter energy density goes down as the universe gets bigger. It does happen, however, in inflationary expansion, because the energy density of the supercooled state remains constant while the universe expands. When the universe doubles in size, the positive energy and the negative gravitational energy both double. So the total energy remains zero. During the inflationary phase, the universe increases its size by a very large amount. Thus, the total amount of energy available to make particle becomes very large. As Guth has remarked, it is said that there is no such thing as a free lunch, but the universe is the ultimate free lunch. The universe is not expanding in an inflationary way today. Thus, there has to be some mechanism that would eliminate the very large effective cosmological constant and so change the rate of expansion from an accelerated one to one that is slowed down by gravity, as we have today. In the inflationary expansion, one might expect that eventually the symmetry between the forces would be broken, just as supercooled water always freezes in the end. The extra energy of the unbroken symmetry state would then be released and would reheat the universe to a temperature just below the critical temperature for symmetry between the forces. The universe would then go on to expand and cool just like the hot Big Bang model. But there would now be an explanation of why the universe was expanding at exactly the critical rate and why different regions had the same temperature. In Guth's original proposal, the phase transition was supposed to occur suddenly, rather like the appearance of ice crystals in very cold water. The idea was that bubbles of the new phase of broken symmetry would have formed in the old phase, like bubbles of steam surrounded by boiling water. The bubbles were supposed to expand and meet up with each other until the whole universe was in the new phase. The trouble was, as I and several other people pointed out, the universe was expanding so fast that even if the bubbles grew at the speed of light, they would be moving away from each other and so could not join up. The universe would be left in a very non-uniform state, with some regions still having symmetry between the different forces, such as model of universe would not correspond to what we see. In October 1981, I went to Moscow for a conference on quantum gravity. After the conference, I gave a seminar on the inflationary model and its problems at the Sternberg Astronaut. Before this, I had got someone else to give my lecture for me, because most people could not understand. But there was not time to prepare this seminar, so I gave it myself, with one of my graduate students repeating my words. It worked well and gave me much more contact with my audience. In the audience was a young Russian, Andrei Linde, from the Lebedev Institute of Moscow. He said that the difficulty with the bubbles not joining up could be avoided if the bubble were so big that our region of the universe is all contained inside a single bubble. In order for this to work, the change from symmetry to broken symmetry must have taken place very slowly inside a bubble. But this is quite possible according to grand unified theories. Linde's idea of a slow breaking of the bubble would have to have been bigger than the size of the universe at the time. I showed that instead of the symmetry would have broken everywhere at the same time rather than just inside bubbles. This would lead to a uniform universe, as we observe. I was very excited by this idea and discussed it with one of my students, Ian Moss. As a friend of Linde's, I was rather embarrassed, however, when I was later sent his papers by a scientific journal and asked whether it was suitable for publication. I replied that there was this flaw about the bubbles being bigger than the universe, but that the basic idea of a slow breaking of symmetry was very good. I recommended that the paper be published as it was because it would take Linde several months to correct it, since anything he sent to the West would have to be passed by Soviet censorship. which was neither very skillful nor very quick with scientific papers. Instead, I wrote a short paper with Ian Moss in the same journal in which we pointed out this problem with the bubble and showed how it could be resolved. Thank you very much for watching. If you want some more videos like this one, please like, share and subscribe to my channel. Have a great day. Stay home. Stay safe.